Okay, 1.15, linear and exponential change. Now, it says here to, um, for each part of the problem, organize the sequence of numbers into a table by pairing the term with the term's number. Treat the first term in the sequence as the zeroth term. Now, I was using the first term because it was just, that's what we used to find the formulas for the nth term. It technically is the zeroth term. Okay, since it is the initial quantity before any changes occur, determine if the sequence is arithmetic, geometric, or neither. If it is arithmetic or geometric, write an expression for the nth term. Write a sentence explaining how the sequence of values is changing within the context given. With real data, sequences are really perfectly arithmetic or geometric, but it is useful to consider the arithmetic or geometric if they are approximately so. All right, so let's go over our two formulas that we have. For the arithmetic from the previous section, to find the nth term, a sub n, or an, we take the first term, we add to it the number, um, the term before the nth term. So n is the nth term, and we want the number before it. And then we multiply it by whatever number we're adding. I'm going to just use a hashtag, number added. In other words, if we're adding 5 to it from term to term, that would be the number 5. Okay, for the geometric was multiplication. So for the formula for the nth term, this time we had a common ratio. We're going to take our first term, and that common ratio was we used little r, and we're going to raise it to the term before the nth term, so raise it to the n minus 1. So that was geometric, and that was the arithmetic. Okay, so let's look at 1a. Suppose Twitter's numbers of tweets in billions per month over a 6-month period, beginning in July of a recent year, were 8. Okay, so they want us this time to start with the 0th term. What, 8.0. This, they call it the 0 term because nothing is happening to this term. So this is actually the first term. They're saying it's because we're adding, in this case, 0.4 to it. So the first term, so this would be July, August, 8.40. And then, see, July, August, September, October, November. So the second term is going to be 8.82. Third term is 9.26. Fourth term is 9.72. And the fifth term is 10.21. Okay, so the question was, is there a sequence to this? Well, let's figure out what's going on here. Let's see, we're adding zero point 0.4 here. Here we're adding 0.42 from the first to the second, 0.42. From the second to the third, we're adding 0.44. So I'm going to write this in pencil because this may not be arithmetic. See, we add 0.4. We're going to add 0.42. We're going to add 0.44. We're going to add 0.46. And then we're going to add point to get from the fourth to the fifth. We're going to add 0.549. Actually 0.59. Okay, so it doesn't look to be an arithmetic sequence. So this is definitely not, oh, by the way, that's 49. I was right in the first place. So this is not an arithmetic sequence because it's not the same number. So let's look at how I could look at this at a geometric. Well, if I, so I'm going to look for something to multiply to get to the next number. So if I take 8, and it looks like I'm going to, I need at least the 8. So I'm going to take 8.00, and I need to at least get the 8. So I'm going to multiply it by 1, and I need a decimal of 0.4. And the only way I can get 8 to be a 40 is to multiply it by 5. But I got to be careful here because if I multiply it by 5, it'll add 40 to that 8. In fact, I'm looking at 40,000, so I'm going to use 1,000th, 0.05. And that gives me my 8.4. So to get from the 0th term to the first term, I can multiply by 1.05. Okay, to get from the first term to the second term, let's see if this works. Times 1.05, and I get 8.82. So it really looks like that it's going to be a multiplication of 1.05. So I'm going to take my 8.82, multiply it by 1.05, and see if I get my 9.26, and I do. And I'm rounding it off. And let's see, let's take 9.26, multiply it by 1.05. I get my 9.72. So I'm definitely have a geometric sequence here. Now, I want to come up with the formula for the nth term here. So I'm going to look over here, my a to the n, or my nth term, is my first term, which is 8 point, um, let's see, should we use its 0th term? Oops, I don't want to use 8. I want to use my variable. So I'm going to use, now you can use a 0th term. Um, I'm so used to putting the 8th term in there, the first term. I'm going to keep using the first term because I've always called this the first term. but technically it is the zeroth term because nothing has happened to that. And our R here, what's our R? What's the common ratio here? Well, the common ratio was 1.05, or the number we're being multiplied to get to the next one. So my R is, and raise it to the n minus 1. So for this particular problem, to write it out, my nth term is 8 times R, 1.05, raised to the n minus 1. Now, don't multiply that out because your order of operations says you got to do the exponent first. But there's my formula for this problem. Okay, let's look at the next one. Suppose the numbers of active Google Plus users in millions per month for over a 6-month period beginning in July. So here's our July, August, September, October, November, December. Technically a 0th term, 1st term, 2nd term, 3rd, 4th, and 5th. Okay, we start at 3.8, 3.68, 3.56, 3.44, 3.32, and 3.2. Okay, so I'm looking at this and it's definitely decreasing. So we're going to be adding a negative number, checking for arithmetic. So if we add a negative, well, let's do this. Let's take our 3.8 and subtract 3.68. So this one we're adding a negative 0.12. To get from the first to the second term, let's try subtract our 3.68, subtract 3.56, I get 0.08. So here we're adding 0.08 to get from 3.56 to 3.44. We're subtracting 0.12 again from 3.44, subtract 3.32. We're adding another point. I'm going to go back and check this one. Let's see, make sure 3.68, 3.56, so 3.68 minus 3.56, 0.12. So this is an arithmetic sequence because every number is the same, being actually it's a negative. So we're adding a negative 0.12. So let's go to our arithmetic sequence. A is an arithmetic sequence. Our formula for the nth term is it's actually the 0th term, but I'm going to use 1. N minus 1 times the number added. Okay, so for my nth term here, First term was 3.8 plus n minus 1, and the number we added was a negative 12. 0.12. So there is my formula for this problem. Okay, next example, next page. Okay, so they want you to keep this in the back of your mind as we go through this section. Determine whether it's a linear function, exponential, or neither from a graph, table, or scenario. How do they relate to each linear and exponential function? And the graph pairs to show linear exponential change. Is that enough to conclude that it does? All right, so let's go through and do some review. Function is a rule that assigns a value of the independent variable known as the input. We all know that the input is our x, the output is our y. Okay. Now, function is an input with more than one output, then the relationship is not a function. We say that the dependent variable is a function of the independent variable, or in other words, y depends on what x is. Okay. Let's look at the example they have here. In the weekly salary S of a coworker who makes $15.75 per hour is a function of the number of hours worked. Okay. So her pay is based on the number of hours she works, where 15.75 is the input. I think I'm going to leave it at that for now. It kind of gets confusing enough as it is. Okay, we often are presented with a situation or problem that we want to understand better. To do so, we determine the variables involved, and then the relationships are used, process known as modeling. Suppose that the owner of a new company has the goal of gaining 500 new customers every fiscal quarter. Write a function to model the relationship between the number of fiscal quarters and the total number of customers. Use table, graph, or an equation to determine how many customers the company should expect to have after 5 years and how long it will reach 400,000 total customers. Okay. Begin by making a table. Okay. You have to make some kind of visual for this in order to organize your data. Now we're going to look at all three of these representation here. Okay, we start with no time having passed for the company and no customers. So no time, no customers. From there, each additional quarter and the number of customers will increase by 500. So this is, again, an arithmetic sequence because we're increasing it by 500 and we're increasing the quarters by 1. All right, looking down the second column on the table, we see that the numbers are increasing by 500 every quarter. Repeated addition can be used in multiplication. The sequence nth term is 0 plus the number being added, which is 500, times n, which can be simplified to 500n. On the graph, we see that for each quarter that passes, the company gains 500 customers. Connecting consecutive points on the graph with the right triangle show that this change is consistent, same shape and size. So the graph is the same information as the table. We can label the expression of the nth term in the sequence, total customers. The equation formed is another way to represent the function. Total customers after n quarters is 500n. Notice in the table that each output is 500 times its corresponding input, confirming our results. The equation can be used to find the number of total customers after 5 years, which is 20 quarters. Be careful here. We're changing years to quarters, so we have to change from 5 years. There's 4 quarters in a year, so we have to use the same label, 20 quarters. Substituting 20 for n in the function, we will find that 500 times 20 is 10,000 total customers after 5 years. The table or graph could be extended using a calculator or Excel to find this result, but the equation provides the most fastest approach in the situation. All right, I think that's enough said. I think you get the idea. Now that is a form of a linear function. Linear function is a function whose output is increased or decreased by a constant amount. Linear function, increase or decrease by a constant amount. And we did that with the 0.12, okay, when we were figuring it out with the other problem. This was a decrease of a constant amount of negative 0.12. Therefore, the function values is an arithmetic sequence. If the function values are increasing, the function represents linear growth. If they decrease, it's linear decay. Okay, in other words, look at the slope of the line. This is linear growth. Slope is going down, that's decay. Okay, let's go to example 2. It says, use the following data to determine if y is a linear function of x. If it is, explain y and write a linear function that models the data. Okay, again, I'm going to use pencil just to make sure. Let's see. Here's my x is 0, my y is negative 18. When my x is 1, I have negative 12, so we're actually adding 6 here. When my x is 2, my y is negative 6, so we're adding 6. When my x is 3, we're adding 1, adding 1, adding 1. When my x is 3, I add 6 to get 0. When my x is 4, I add 6 to get 6. So I definitely have a linear growth. Linear model, and it's growth. Okay, what else do we have? Explain why and write a linear function that models data. So when my x is 0, okay, so when my x is 0, I'm adding to it negative 18 is my y. I'm sorry, I'm adding to it 6. Not negative 18, that's my y value. I'm adding 6 to it. And it depends on which position that is, where my n is. Okay. In other words, this would be my n equal 1, n equal 2, n equal 3. We can actually, so that equals my nth term. We can actually reduce this. See 0 plus, so 6n equals the nth term. So there's my model, 6n. Pretty easy. Let's try another one. You have an interest-free loan of $800 you're paying off at a rate of $50 per month. Model the situation with the table, graph, and the equation. Is the function linear, equation, function? How many months will it take to repay the loan? Okay, so month M, I have $800 to pay. So at 0 months. 1 month, I'm gonna pay, what am I paying? 50 bucks. I have 750 bucks. 2 months, pay another 50 bucks. 700. 3 months, 650. 4 months, 600. 5 months, 550. Okay, so my equation here is 0 minus or plus a negative 50 bucks, depending on that number. Okay, so let's see. Sorry, this would be 800. I should have did that up there too. Okay, so let's see, 800 minus 50n when my n is, so yeah, okay, so they want to know when this is going to equal 0. The only way that'll equal 0 is when this equals 800. So my 0, I put my 0 there, and I'm just going to solve this equation. Let's see, I'm going to subtract 800, subtract 800, gives me negative 100 equals negative 50. And because I'm trying to find the number of months it's going to take me, divide by negative 50. 800 divided by negative 50 is going to be, try 800 this time. It's going to take me 16 months. 0 going to equal that. That's 16 equals that. So it's going to take 16 months to pay it off. All right. Let's see how many months we played. Got that answered. Got the table. I need a graph. Here's my equation. So I just need a graph. Let's see. I'll put my months. One, or you could put July. Let's see. 50, 100, 150, 2. So I'll put my dollars here. 250, 3, 350. I'm gonna kind of shrink it up here. 4, 5, 6, 7, 8. So 0, 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. All right. 0, 800. Let's go 2, 700. 3, 650. Well, I'm gonna go out. Let's go out to 5, 550. And if I had this all scaled right, I would have a straight line. This axis down here to 60. Next step, I'll use graph paper. Okay, linear functions are useful for modeling situations with changes that are consistent amounts. Again, there's that key thing, consistent amounts. Some situations involve change that is not consistent amount, but rather a consistent percent. Let's look at this kind of change and type of function used to represent it. Okay, so the next function we're going to look at is the geometric function, right? A virus is contracted by 100 people, each who infects 2 more people the first day. So another way of saying this is it doubles. After which they are no longer contagious. Write a function and model the new number. Now, this is the way they did it. Drew a picture. So the first person, contagious, patient 0, double it. Okay, they get 2 people. Double that, they get 4 people. Double that, they get 8 people. So what's happening here in the table? It's being multiplied by 2 to get from 100 people to 200 people to 400. So it's doubling. And this is the way it would look on a graph. If this were my X, this were my Y. Let's see, 0, 100. Looks like it would start out linear, but then it doubles here very quickly. And that's where we get that exponential growth here. Now the nth term is going to be that what it was first day times 2, our common ratio, and raised to the n for the nth term. So that's where they got that equation here, or the sequence equation, 100 times 2 to the n. Okay, so let's keep going. So the nth term, by the nth day, we're going to have the equation is going to equal 100 times 2 to the n. Now, suppose they wanted to know how many people are going to be infected by the 14th day. All she would do, substitute in 14 for the n. So 100 times 2 to the 14 gives us 1,000,000.6 new people infected. To find out how long it reached to take 100,000, use a calculator, extend the case. Now, what I do? Put 100,000 equals your 100 times 2 to the n. Okay. Um, if you don't remember how to do that from algebra 2, then you would have to do it this way. You would have to just keep extending the table on the graph, or put this in a calculator, your y equals buttons. There's a couple of different ways, but they're telling you to go ahead and keep doing it over and over again, the doubling until you got to 100,000. I'm going to show you different kinds. Anyway, geometric sequence is called that exponential function. Okay, you're either going to have, just like we did with the linear function, you're going to have exponential growth and exponential decay. Okay, so this is actually pretty good. The dependent variable, and that's the equation he gave you up here. That's the dependent variable. The dependent variable is going to equal the starting value, or your zeroth term, times r, your common ratio, the multiplier, times your x value, or your independent variable. So that's actually, we were putting this in x and y. Your first term, or zero term, times r to the x. Just another way of thinking about it. Okay, let's do an example. Did I skip some three? Okay, they're just stating here, some functions are not exponential, but can have similarly shaped graphs. Okay, company wants to project, let's look at number 4. Company wants to project growth using both linear and exponential change to see long-term effects. The company begins with 150 clients. CEO wants to project growth, assuming 15 new clients per month versus a 10% growth per month. Model each situation with a function. How many months will it take the company to reach 500 clients with each approach? Okay, so let's look at the first one. We're adding 15. So to get, what do they want? 500 clients. So there's our y. So both of them are going to have 500. Okay, for the thread sequence, begins with 150 clients. And we want to add to it 15 new clients per month. Okay, that's solve for n. Subtract 150, subtract 150, so 350 equals 15n. And 350 divided by 15. So I'm going to divide both sides by 15. So it's going to take approximately 23.3 months to get to the 500 clients. Now, let's see exponentially. 10%. So I start with our 15 raised. I'm going to multiply it by our common difference, 10%. raised to the n. Instead of 10%, I'm going to use 0.10 raised to the n. I'm going to get rid of the 15. Divide by 15. Get 33.3 equals 0.10 raised to the 10th. Oh, wait, something's wrong. Made a mistake. Should be 15. We started with 150. So I forgot a zero here. Now I need to erase my 15 here. Okay, so this should be 150. All right, so what I'm going to do is I'm going to put this in my, I'm going to make a graph here. So I'm going to put in my y equals 150 times my 0.10. Now I don't have an n, but I do have an x. So raised to my x. I'm going to graph. Don't forget, this is my y value. So I'm going to look at my table in my calculator. So I'm going to hit the second button, graph, to get my table. And when my y is 500, that is going to tell me what my n is. This should be growth. Why am I getting? So we want to take our 150. I'm going to do this a different way. We want to take our 150 here first, and then we're going to add to it 10% of 150. And before we get into any graphing calculators and stuff, they want us to figure out, well, keep doing this over and over again in your calculator until you get to 500. So also I'm going to do 10% of 150 is 15. So it comes out exactly like the arithmetic sequence. So it doesn't, they're really trying, it was a bad example, and they're just trying to trick you. Okay, so I don't like this one, so let's try the next one. Okay, so to we're going to go back. They're trying to explain how these geometric and arithmetic sequences um, fit into exponential growth and linear growth. You've done this before, okay? We know that linear growth, linear, which means line, growth or decay, its equation that you guys are used to is y equals mx plus b. Okay. Um, where m is going to determine whether it's growth or decay, depending on the slope, right? That's what m. If it's negative, it's decay. If it's positive, it's growth. Now, to brush up your memories, the geometric sequence that they're using up here is exponential growth and decay. Back from algebra 2, even algebra 1, I think you guys covered this, is y equals a to the 1 plus or minus, depends, growth is plus, decay is minus, times the rate raised to the x. Now I'm going to put x here. Sometimes you put time. I put x because that's the key we have in our calculator. Excuse me. Okay, write a function. So I'm going to use these two functions. Population increases by 5,000 residents per year. Okay, let's see what we got here. We have 1,000 residents. So now there's our, um, we don't know whether it's linear or exponential. So we got 1,000 residents are modeling the population in various ways to help them make decisions related to resources. Experts disagree on the growth rate and model. And since they are using different data, but they do not have the resources for only 200,000 residents. For each scenario, write a function and use to determine when the city will be at its maximum capacity. So their maximum capacity is 200,000. Okay. So for the maximum capacity, we're always going to have the 200,000. That's going to be our y because we can't go any higher. Now, our initial um, residence amount is our A in the exponential model and is our B in the linear model. So let's see if write a function, 200,000. If it increases 5,000, that is definitely an arithmetic sequence, a consistent, constant increase. So I'm going to use the linear model. Our B starts at 100,000. I'm going to put that one in first. It's easier. Okay, so my slope here is the increase, which is 5,000. And instead of X, I think we were using N, but I'll use the X. Okay. Now remember, we were just doing this. Remember, they had us make a table, 0, 100,000, and we were figuring out arithmetic sequences. First year, we added 5,000, at 105,000. Second year, we had another 5,000, so it was 110,000. Third year was 115,000, where we were adding 5,000 was our consistent, right? So our nth term here would have been, start with 100,000, and we add to it the nth term, and our common difference was 5,000. So that's where I just took a shortcut. I just took a shortcut using the y equals mx plus b. My y was the 200,000 maximum capacity. My slope was the 5,000 that we added to each for the sequence. And then instead of the n, I used an x. So they want us to self-rex. So I would subtract 100,000 from each side. You got 100,000 equals 5,000x. Divide both sides by 5,000. So x is going to equal 20 years. Okay. And you would do the same thing because this, again, is using a constant change. Okay, so it's a consistent constant change. So again, we would use our 200,000 equals, instead of 500x, I'd be using 8,500x plus we start out with 100,000. Subtract 100,000. I get 100,000 equals 8,500 x, and divide both sides by 8,500. And I don't know what 100,000 divided by 8,500 is. About 11 3/4 of a year. Or 11.75. Now this one increases by percentage. So I'm going to use instead of that whole geometric thing like we did up here where it's really confusing, ended up to be the same. Let's just plug it into our exponential growth and decay formulas. We have them, let's use them. Okay, our population, again, our initial population is A times 1 plus the rate. Now, to change this from a percentage to a decimal, move that decimal over 2 places. I have 0.25 to the x. Okay, and I'm going to plug this into the calculator in my y equals button. I have 100,000 times 1 plus 0.025 raised to the x. I'm going to graph it, let it graph. And I'm looking for when y is 200,000 because that's our max. So I'm going to go to our table, second graph, and look for that 200,000 for my y. Remember, y equals 200,000. Scroll down until I get to the 200,000. It's got to be at least 200,000. So it's going to be when my X is 29. So in other words, 29 years. All right, going to do that again. Initial population A is by 100,000 times 1 plus the rate. This time the rate's 3%. Move your decimal over twice. 0.03 to the X. So I'm going to go to my Y equals button on my calculator. Going to put in 100,000 times 1 plus 0.03 raised to the X. Graph it. Don't really care what my graph looks like. I want the table. Second graph brings up my table. And I want it when my Y value is 200,000 at least. Oops, didn't put enough zeros in. So I'm off at 0. So instead of 20,000 or 200,000, I'm going to look for 20. So right there, 24 years. Much easier to do it with the exponential growth and decay formula. Okay, that's it. So you should be able to do this, your homework from the examples I gave you. As always, any questions, please email me.